whenever if you draw current, voltage and current, for example, this is the V in, that's a forward bias voltage, and this is a current. So for a diode, ideally, there shouldn't be any current until this point, until this threshold voltage. Okay, and this voltage is 0.6 volts. So after this voltage, even though you are increasing your V in, but voltage shouldn't increase anymore. So the way it keeps the voltage constant is the diode is going to run a lot of current. So it won't be perfectly straight. So it becomes this, actually. It's very similar to the VGS to IDS curve of the CMOS transistors. But it won't be perfectly straight. It will be something like this. Okay? So whenever you are increasing your V in, the way that this guy is trying to drop a constant voltage is to run a lot of current through it. So that's how that works. So this is the IV curve of the diode. IV curve of the diode. It's still too ideal. So in reality, it looks like this. You know, there will be a little current going through it, even though it's tiny. So this is 0.6 volts. That's V in or V forward bias. Okay, and this is I of the diode. So there's another type of diode. It's called Zener diode. So Zener diode cannot be used as a diode. Keep in mind. So Zener diodes are used as a voltage stabilizing device because we don't really use it under the forward biasing condition. So it's usually like this is a regulator, plus, minus, and just in case there's a surge. Okay. So we keep a Zener diode here, and it's being doped in a certain way that is able to allow a reverse bias, and it's going to stabilizing the current as a voltage at a certain point, depending on the concentration of the doping. So what's happening is the IV curve of the Zener diode is like this. So whenever it goes to the negative region of the V in, which means this part is reverse biased. So keep in mind, Zener diode is, I've never seen it's being used in the forward biasing situations. It's always been reverse biased. Keep in mind. So sometimes I have all the different components in the drawer in the lab, and students were trying to search for some diode to be used for their power circuit, and they couldn't find it, and directly grab a Zener diode from the drawer and plug into the circuit. That shouldn't be used that way. So Zener diodes are always being used as a voltage stabilizing circuit. So because of the doping concentration of the pin junction of the Zener diode, you can have a different voltage here. So for example, this one is 3 volts. Okay, so negative 3 volts, but the thing is, since you are reversing, connected reversely, that is why this guy is plus minus negative 3 volts, right? So what's happening is it's plus minus 3 volts. You know what I mean? So it's trying to avoid surges, any surges. For example, I'm trying to give a 3 volts output. That's the voltage regulator's output. I want to power up my circuit, including a lot of things. Okay? So the problem is, who knows, like if this one fails, and there will be a surge. So it should be 3 volts always, but there is a surge. What's going to happen? You look at this one. Whenever the surge comes, it's actually the reverse biased voltage. It's going to the negative region. So whenever the voltage is going into that direction, which is a surge, okay, what's happening? It draws a lot of current, trying to pull the voltage back to 3 volts. So you can see it's on x-axis. It's not really wiggling a lot because the current is so huge. Its current gain is so large. Whenever it's trying to move to the left a little bit, it just draws a lot of current to pull it back. Okay, so eventually stabilize it at 3 volts or negative 3 volts, but forward biased. But now I'm reverse reverse biasing these guys. That is why eventually I'm getting a plus minus 3 volts at this point. So eventually, it's helping this voltage regulator to avoid any surges and to protect the circuits after that. So Zener diodes are being used in this way, but not here, not like this, or any other purposes in the circuits. Keep in mind, don't just randomly grab a Zener diode from the drawer and tell me that you don't have any like other diodes options. So pick up a Zener diode. That doesn't make sense. So Zener diode is being used as a power supply. So you can have a different ones. For example, they can stabilize the voltage at 5 volts, 6 volts. You just search in Amazon, you can, or DigiKey, right? You have all different options, So in that case, we know that Zener diode is being used. So we use the negative region for the Zener diodes, and we use this part for the regular diodes. And we can use the regular diodes to form a clamping circuit, because it's able to, since it's dropping a constant voltage, so we can use it. We can use it to clamp the voltage at a certain range to avoid surges as well. But we need the 2 diodes in a pair. So let's look at this example first. Plus minus V in, plus minus V out. So if I increase V in, can you plot V out for me? So V in is not V out because there's a resistor dropping the voltage. So V in and V out are not equal. And whenever V increase, so the voltage drops across the diode will increase as well. And at the point, it runs current through it. And then this guy will drop a certain voltage, which is 0.6 volts constantly. Okay? And if you look at the nodes, the two nodes of the diode are the same 2 nodes of the V out. So eventually, this voltage equals V out. So how to draw the curve? When V increase, V out equals what? So when V in increase before it reaches 0.6 volts, what V out looks like? Yes, the same way. Because there's no load. Did I connect any load to it? No load. And this is below its threshold voltage, and we assume that there's no current and no voltage drop. Right? Oh, there's a voltage drop, but the thing is no current, so it's okay. No current, which means there's no current here as well. You don't have anything connect to the nodes, do you? No, nothing. And before it reaches the, 0.6 volts for the V forward bias and I of the diode, there's no current. Okay? No current means no current. And no current here means no voltage drop. So that means V in equals V out. Does that make sense? So that's why it's a linear curve. But after 0.6 volts, what's happening? After 0.6 volts, it got current, right? It got current. But stabilizing V out at 0.6 volts, is it changing after this for V out? No. What about reverse biasing? So whenever the voltage becomes negative, which means this voltage is negative, or you can say this voltage is positive, right? So it's reverse biasing this guy, and you are not getting current at all by reverse biasing it. The ideally, right, at a certain point, it's going to penetrate this diode. If you reverse bias and give it too big, the voltage is too big, larger than the limit, it's going to break it down and you cannot recover it. So that's the regular diodes, right? If you have a Zener diodes, the Zener diodes are being designed for reverse biasing. So that's why at this point it breaks down, but after you reduce the voltage, it recovers. That's a Zener diode. Okay, because we use Zener diodes at the breakdown state. It reverse breakdown at this point. Okay, but for regular diodes, you reversely break it down, and you cannot recover it. It's damaged. So we assume that we don't give a huge voltage reversely. So, but you know, it's negative voltage over here. Your VL is gonna duplicate the voltage because there's no current, no voltage drop. So eventually it's a linear curve. Does that make sense? All right. So what about this? Second situation here. V in V out like this. Is that something I want to do? Yep. What is the V in and V out curve? When V in is positive, diode is getting reversely biased, so there's no current always, as long as you don't damage it. So V out is going to duplicate V in because there's no current. Right? And whenever it reaches what? Whenever this voltage reaches negative 0.6 volts. This one becomes forward biased and it's dropping a constant 0.6 volts. And because same nodes, so VL becomes negative 6 volts. Constantly, it's not changing anymore. Does that make sense? Then we look at another example. How about this one? So whenever Vi is larger than 0.6, this one has current in there, so stabilize it at 0.6 volts. And whenever this is smaller than negative 0.6 volts, and this one has current, go through it, so it's going to stabilize VL at negative 0.6 volts. So eventually it looks like this. V in, V out. So that's called, it's getting clamped at these two voltages. Okay. Why is this useful? Because, for example, the chip has all these inputs, and there's a ESD protection circuit. It's being formed by these circuits. And here's a V in as a resistor to limit the current. And before you inject any voltage into the pads of the IC integrated circuits, and you have these two diodes connected in this way. And for example, it's a 20 volts power supply for the chip. Okay, what are the possible voltages you can get in to the chip, or the chip is going to receive? So the goal is not to get anything larger than 20 volts or negative 20 volts, for example, or maybe 25 volts, let's say. That's the voltage rating of the chip. So if this one is larger than 20 volts, 20.7, like let's say 20.7, what's going to happen? 20.7 volts, 20.6 volts. So this diode will be forward biased, even though you have a cathode, have a 20 volts for the cathode. But the thing is, 20.6 minus 20 minus 20 volts will be 0.6 volts. It's exactly the voltage dropped by this guy. If you have like 21 volt, what's going to happen? 21 volt for the input, like a surge at the moment. It's not changing. Why it's not changing? Because this is the power supply super strong. What is this guy dropping? Okay, since this is super strong voltage, 20 volts, and you know that this guy is dropping 0.6 volts, so what the voltage here is, exactly. KVL, okay, KVL. 20 volts here. 20 volts is what? It's like this, right? Plus minus 20 volts. That's a power supply. Plus minus 20 volts, minus plus 0.6 volts is fixed. So what's the possible voltage here would be? It's exactly 20.6 volts. It's not changing. You're asking, how is that possible? If I got a surge like 20 volts or like say 40 volts. 40 volts. It's a surge, okay? What's the voltage? I mean, 40 volts for V in, but there's a resistor to drop the voltage. But eventually, the voltage at this point will not be higher than 20.6 volts. How is that possible? I got 40 volts surge for V in accidentally, and eventually, because you have this circuit, and this point will never be larger than 20.6 volts. It's protecting the IC over here. Why that works? Where's the current? Where's the voltage going? Where is it? How did I remove the surge by this circuit? Does anyone know that? No? It's just gone? The critic told us it's gone, it's gone. Who cares? Oh, it's on the quiz? Let's think about it. So because this guy is constantly dropping at 0.6 volts by drawing a lot of current through it, so whenever you got a surge, what's happening is this one will reduce its internal resistance and draw a lot of current through it. Okay, so when the current is large, because you have a resistor here to limit the current, so the current goes through the resistor, will create a large voltage drop. So eventually, the 40 volts will be mainly dropped across this guy, the resistor. That's why we need the resistor here. You know, so the diode, because the voltage, so very short period of time, you got a surge over here, reaches here, and it creates a pretty big voltage drop, and that one introduces a lot of current into the diode, and that current will go through this resistor and create a drop, and that drop, so all the 40 volts, most of the 40 volts will be dropped across the resistor, and so eventually give you 20.6 volts fixed over here. And you're asking like why it knows that it has to be at 20.6 volts. It's because you have a really powerful DC power supply, and which has a zero internal resistance. So that's why it allows current to goes into that power supply, going this way. So it eventually flows through that power supply and reaches the ground, which is fine, okay? And because we know this is an ideal power supply is 20 volts, right? So it's dropping 20 volts from here to ground. It's dropping 20 volts. And we know this is fixed as well. It's dropping 0.6 volts. So eventually this node has to be 20.6 volts. There's no other choices. What about this part? What about this part? So whenever you have a voltage lower than what? The surge can go down to negative as well. Let's say you have a negative voltage, like negative 20 volts. What's going to happen? Because you have 20 volts here and negative 20 volts here. Is this forward biased or reverse biased? That's the question. Is this guy forward biased or reverse biased? Reverse biased, because you have higher voltage at the cathode. Okay, so there's no current, so this one is not working. Okay, what about this guy? Forward biased. Okay, forward biased. What's happening? Yeah, so it's higher than negative 20 volts. So negative 20 volts is a pretty big negative surge, negative voltage surge, and can potentially damage the chip as well. Okay, it's a big voltage, even though it's negative. So the thing is, this diode will be forward biased, and it's gonna drop a constant voltage, for example, 0.6 volts, for a certain process. Okay, doping concentration will make it 0.6 volts constant, dropping here. Okay, so what's the voltage here? We're saying like negative 20 volts, negative 40 volts. Is it going to make a difference for this voltage? Why? Yeah, current changes. So the difference is this one is generating different amount of heat, right? Or different amount of current running through the resistor. But the thing is, this voltage doesn't change because you know this voltage is fixed. So like the power supply 20 volts is fixed. Its ideal power source is not changing. Like this 0 volts as well as a ground. It's part of the power supply, right? It's going to be permanently 0 volts. And you know this is 0 volts, and you know this is 0.6 volts drop. So exactly you know the point here is what? It's a 0 minus 0.6, right? It's negative 0.6 volts. And cannot go lower. Cannot go lower because of the clamping circuit. So eventually, no matter whatever surges you have for the input, since you have this circuit with a resistor and two diodes, so it's clamping this point at what? What's the range here? That's the lowest and highest possible voltages for this node. And given that the chip cannot handle anything lower than negative 1 volt or positive 21 volt, and this one falls into the range. Okay? Happy. It's protecting the IC by using this ESD protection circuit. Okay? Any questions on this? I think we'll take some time to draw a pad of the, remember the over glass pad? Okay. We got P-sub, poly, Fox, poly, metal 1, metal 2, metal 3. So that's what's that called? Over glass? Forgot. That's the opening. So this is called passivation. It's a passivation layer. It's also a silicon dioxide. But the thing is, you can have an opening on the top from one of the masks. It's a device from the library, and you can open it up on the silicon dioxide. So this one exposed to air. That's metal 3. Okay, that's a pad. It's called pad of the chip, and that pad has to be ESD protected, which is this guy. Okay, so here's a pad, for example, and it has to be ESD protected. So we have to put a circuit in here. It could be metal 2 or metal 3, doesn't matter. So all these voltages being injected into metal 3 has to go through this thing before it goes to the chip over here. Okay. I think that's it. Any question on this? So we'll probably do the quiz on Monday. Have to cover more about all the layouts and AOI Logic, how to form NAND gates, NOR gates using transistors, and then we'll do a quiz on Monday. Okay. See you later.